modus tollens. And so it's not true that your language is regular, therefore it's non-regular, and that's how you prove it. So that will be the pattern throughout these 5 examples that come after we complete the formal proof, the detailed proof of the pumping lemma. So that gives you a sort of feel for what the pumping lemma does and what it's about. So, okay. Well, we're in the mid. We're still. We've got another square or so of discussion on the overview, the proof idea. We're trying to show why the pumping lemma works, and we got as far from, if you remember, towards the last session. Let's see, what did we do? We had, well, I can probably revise and probably kill 2 birds with 1 stone. Now we got to the point we had an input string S. We assumed that the language was regular, okay, and because it's regular, therefore you can use the pumping lemma, okay, because the pumping lemma is appropriate when your language is regular. Okay? So, and our pumping length. Well, let me just state the pumping lemma again. Refresh your memory. So, if a language A is regular, then you can find an integer, a non-negative integer, call it little p, and it's called the pumping length. So just think, there is this integer, such that, so that for all strings belonging, all strings S belonging to your language A, they can be split. So all those strings that are greater or equal, whose length, the length of those strings, is greater or equal to this pumping length, little p. So all those strings that are sufficiently large, right, their length is greater or equal to little p, the so-called pumping length, then those strings can be split into 3 parts, 3 substrings if you like, x, y and z, such that you can pump these strings, and that the pumped, the result of the pumping, the pumped strings also belong to the language. They belong to A. Now, pumping, what is that? To pump a string, what are you doing? You take this split string S, that's split into 3 parts, contiguous parts, x, y, z, and you can make multiple copies of the y and insert them in the middle. So, so the string you start with would be, sort of like, here's the x part, here's the y part, and here's the z part. Okay, and a pumped string, you would have multiple copies of the y part. So you might have x, x, y, y, multiple times, y, 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 and then z. Okay, that's a pumped string, and that string is also a member of the language. Okay, that's and there are various conditions on this pumped string, x, y to the I, y to the I. That means I copies of y, z. 3 conditions on this pumped string. The main one is that the pumped string, so x, y to the I, z, that pumped string belongs to the language, first condition. Second one is the size of y has to be positive, can't be 0. And the third one is that the size of xy has to be less or equal to the pumping length. In other words, less or equal to a little p. I think that's correct. I Yes, here it is here. That's the third condition. So there are three conditions on this pumped string: x, y to the I, z. Okay? Alright, now jumping ahead a little bit. So you'll use this pumping lemma to, via a proof by contradiction, you will use this lemma to prove that certain language, that a language is not regular. And how will you do that? Well, by finding, by contradiction. You only need to find one counterexample. Now, see, the pumping lemma says that if the language is regular, you can find an integer positive, non-negative. You can find a positive integer p, call it the pumping length, so that all strings in that language, S, all those strings, S, in that language that are greater or equal to, that their length is greater or equal to little p, pumping length, then all of those strings, S, satisfy those three properties, those three conditions. Okay? So if you want to show that a particular language is non-regular, all you have to do is find one counterexample, and that kills the notion of that the language is regular. Because if it is regular, all strings, and that's the point of the pumping theorem, all strings, that satisfies those three conditions, the length of those strings is greater or equal to little p, the pumping length, then all of them will satisfy those three conditions. The first one, that the pumped string belongs to the language, the size of y is positive, and the size of x, y is less or equal to p, those three conditions. So if you can just find one string that for which those three conditions, or just one of those three conditions, is not satisfied, well, then you've got yourself a contradiction. You've got yourself a counterexample, right? And that's all you need. If you want to kill a theorem, just find one counterexample. That's enough. So you find a counterexample. So proving, these 5 examples that we'll do, you just go trying to find one counterexample. In other words, one string that is larger than little p and cannot be pumped. Right? You just find one counterexample of a string that cannot be pumped, and therefore you've got a contradiction, and therefore the pumping lemma is false given that counterexample, and therefore your original assumption, by proof by contradiction, therefore the original assumption is false. And what was that original assumption? That the language is regular. But you negate that, therefore the language is non-regular. And that was what you wanted to prove in the first place. Okay? So that's sort of the bigger picture. Alright, now we're still in the proof idea. We got as far as we were showing how to split your string into x, y, and z. The y, we had a sequence of states that the machine was going through, and we were saying, like, we proved. Let's see. We let little p be equal to the number of states in the machine, right? And therefore the number of states the number of little p we let to be equal to the number of states in the machine. We input an input string of length n, little n. Okay. So I'm just trying to refresh my memory, my own memory from a previous session. So we input a string with n symbols in it, right? Length n, and therefore the sequence of the states that the machine went through by the time it finished, once it had read the last input symbol in the string, it had been through n+1 states, right? So we assume the starting state was Q1, dot 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 right to the end, and we finished at Q13, say. Since that input string is accepted by the, because we're assuming that the language is regular, okay? Therefore, this machine recognizes that input string. Therefore, the last symbol in the string is one of the accept states of the machine, okay? Of the DFA, call it big M for machine, right? And we so the sequence of those states, it's a DFA, right? So there's only one next state all the way through. Now, but the number of those states in the sequence was n plus 1, okay? But there's only what did we say n was? We let n be I'm getting a little confused here. The difference between n and p. Was it n or p was the number of states in the machine? Was it n? I'll need to come back to that. That'll clarify as we get through it. Anyway, what we showed was there were more. The length of the sequence of the states was one more than the number of different states there are in your big queue, for your machine. Therefore, there has to be at least one repeat, at least one of those states in that sequence of states as the machine reads through your input string. At least one of those states has to be repeated. Okay, so we just arbitrarily let's say, okay, let that state be Q9, right? And so you'll have a list of the sequence of your states will be something Q1 dot 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 Q9 dot 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 Q9 again dot 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 dot, and so that allowed us to that was the sequence of states from time going this way, and correspondingly we had the input symbols that generated those next states one by one, and so we developed